Can start.
Cool. Hey everyone, we are Group 1. We're here to present our final deep learning project. So the whole project is divided into two tasks. One of the tasks was to weather forecast 12 hours ahead on a data set called Jena. We'll talk about that in a while, using sequence models like RNN and LSTM. Followed by the task 2 will be presented by Avishkar, where we understand how CNN works underneath and try to visualize the filters and the feature maps. Starting with the agenda. So task 1 mainly focuses on forecasting temperatures 12 hours ahead using sequence models and comparing that performance with the baseline models, which is going to be the persistence, moving average, along with the recurrent neural networks. Task 2 will be primarily involved in understanding how a CNN works underneath and how does it learn on a data set called CFAR10 and evaluating throughout using loss curves, parametrics, and confusion matrix. So we started with the data set called Jena, which is roughly captured between 2009 to 2016. It captures a temperature along with several other metrics every single 10 minutes. We converted that data into hourly basis and overall reduce the data points to 70,000. The target was to predict the A temperature 12 hours ahead. And you can clearly see that in the graph over here on the right side, there's a strong seasonality after every single year as well, and every single 24-hour time limit. So this is how we started with our pre-processing steps. So we split our data set into 70s to 15 and 15 ratio. The 70% is mainly for the training part, and the 15% is mainly for the testing, and the 15% remaining is for the validation part. We didn't shuffle the data set primarily because if we shuffle, since the data is by default time series, and we have to weigh the time series stuff. So if we try to shuffle the data set, it might lead to peaking, I would say leaking the values of the future, and it would not let the model learn better and might overtrain and overfit as well. We standardize the whole thing using mathematical statistics using mean and standard deviation, and the metrics were reported back in degrees Celsius. We also involved sliding windows like last look back hours, which is an ablation technique. We'll talk about that in a while. So there were three approaches that we started with. The first one was the baseline model, which was basically persistence. What it means is it tries to predict the next day's value, which is equivalent to the recent value or the previous value itself. And the moving average is basically the average of all the values over a certain window or a threshold. There is no learning involved over here because the model doesn't learn anything. It just predicts purely on the basis of mathematics and basic probability. The vanilla RNN, on the other hand, involves 64 hidden layers, which is basically a neural network called recurrent neural network, and it understands the stuff. And most importantly, LSTM is built on top of vanilla RNN, which also has several memory, much more memory bandwidth as compared to the recurrent neural networks, and hence it allows to hold the context for much longer and for larger amount of time as compared to the traditional recurrent neural network. Starting with understanding why did LSTM beat the other models. So LSTM won mainly because, as I said, it has much more memory bandwidth as compared to the traditional recurrent neural network, and it definitely beats persistence as well by 48% because there was no learning involved over there. It was just pure prediction on basis of probability. So LSTM's prediction approximately was around 2.81 when it comes to root mean squared error as compared to 2.86 with RNN, and much higher as compared to the persistence baseline model. Persistence is a full half day out of the phase at 12 hours window. Followed by this looking at the different window lengths. We experimented with different window length, starting with the 6 hour, going to 12 hours and all the way up till 96 hours. The reason 6 hours fall too short was primarily because it didn't capture the data points and the variations, specifically temporal spatiality, pretty well, whereas 12 hours worked pretty fine because it captured one day cycle window, and the performance of LSTM pretty much peaked after 20 hours, whereas RNN kind of plateaued, and LSTM kept improving till 96 hours. And that's the reason the overall performance is better as compared to all the other models. Now, I would hand over the presentation to Avishkar to explain about the CNN.
Thank you, Rihan. For task 2, our goal was not only to train a CNN, but also to understand what it learns internally. We used a CIFR 10 dataset, which contains 60,000 color images across 10 object categories. We designed a small VGG-style CNN consisting of 4 convolutional layers followed by a fully connected layer. The network contains approximately 2.3 million parameters. Next slide. After training for 12 epochs, the model achieved approximately 82% test accuracy. The loss curve decreases smoothly while the accuracy curve steadily increases. The small gap between the training and the testing performance indicates that the model generalizes well and is not significantly overfitting. The confusion matrix helps us identify where the model makes mistakes. Most errors occur between visually similar classes. For example, cats are frequently confused with dogs, and cars are sometimes confused with trucks. Classes such as ships and airplanes achieve very high accuracy because they have more distinctive visual features. This behavior is consistent with typical CNN performance on a Cipher 10 dataset. Next slide. Here, we visualize the first convolutional layer. These 32 filters are applied directly to the raw image pixels. Instead of recognizing objects, they learn simple patterns such as edges, color transitions, and texture directions. These low-level features form the foundation for deeper layers to build more complex representations. Here we com- Here we compare feature maps from an early layer and a deeper layer. Early layer preserve detailed information such as edges and object outlines. As we move deeper into the network, feature map becomes more abstract and focus only on the most informative regions. This demonstrates how CNN gradually transforms from raw pixel into meaningful semantic representations. The next slide. Our visuals reveals a clear hierarchy of learning. For the first layer, dated simple edges and colors. Intermediate layers combine those features into textures and shapes. Deeper layers capture object level concepts that are useful for classification. This provides insight into why CNNs are so effectively at image recognition tasks. Next. So to conclude, in task 1, LSTM achieved the best weather forecasting performance and showed a stronger long-term memory than a standard RNN. In task 2, our CNN achieved around 82% accuracy on Cipher 10 dataset, and the visualization demonstrated how representation becomes increasingly abstract with depth. And thank you for listening. That's conclusion.